Um, so we are in the middle of rigid body kinetics. I did the example last time of different round shapes rolling down an incline. Today I'm going to do a pulley with size and mass. And then the third one I think I'm going to do is, you know what the Pinewood Derby is in Cub Scouts? Really nice. Well, so there's sort of a weird thing about that. You know, Pinewood Derby is this, you have a block of wood, you can shape it however you want, and then just some cheap little wheels connected to it, and you roll it down an incline, and you race against other people. And what we know, like very basic analysis of sliding without friction says that the mass of a block sliding down an incline isn't going to have any effect on how much it accelerates down the incline. Something that has a mass of a ton is going to be the same as something that has the mass of an ounce. And the rolling thing that we did, when we looked at the equations, we saw that the shape of the thing that's rolling affects acceleration, but the mass of the thing and the size of the thing does not. Sort of surprising. So, okay, Pinewood Derby is a combination of two things. I mean, you could think of treating it sort of two different ways, right? You could think of it as something just sliding down the incline and ignore those wheels there. Or you could think of it as those wheels going down the incline and ignore the thing on top. And both of those two ways of thinking about it suggest that the mass shouldn't have any effect. But in reality, the mass does have an effect, and there's a limit to how much mass you put on there. So we're going to do a more careful analysis of this Pinewood Derby car idea and get a final equation that shows that the acceleration is dependent on both the mass of the block and the moments of inertia of those wheels, and we'll see how they relate. And then that will give us some ideas about how to dominate, how to beat Mike's Pinewood Derby. You still have it? We should try to beat yours at the end. Yeah. So these are sort of three long examples, Pinewood Derby. We've done this one. So what are you supposed to get out of these examples? What I want you to get out of these is, I mean, they're sort of things that you might have wondered about briefly at some point or another. But mostly they're just different applications of those steps that you should follow for rigid body dynamics, kinetics. So it's not really these examples that are important. It's being able to apply the steps for rigid body kinetics to a few different types of questions. Okay. So always the same steps, and I try to bring out the steps as we go through. Yep. Nope. Friction, though, comes in sort of a boring way. Friction just adds a certain couple, and so you just add on another couple to the problem. That's easy to deal with. A little more complicated can be the mass of the cable, and we're not going to deal with that, but that's not too terrible either. All right, so the next example. So we want to compare the accelerations. The first one is a pulley. Well, let's just do it with, let's have a lighter mass and a heavier mass. So I'll call the bigger mass, capital M, the little mass, lowercase m. And we'll assume that that pulley is massless. And then in the second example, we'll do the same thing. Why am I drawing it again, you might ask? I'd like to turn back now. But this time, the pulley is going to have a moment of inertia I sub c about its center. No, that is friction. The bearings basically reduce the friction to almost zero, but that doesn't change so the mass is just like weigh the pulley. How significant is the mass of that pulley compared to the masses of the things? If you took physics 1 here, you probably did labs with those little tiny plastic pulleys when you spin them and they just spin forever. Because those are plastic, they don't have much mass compared to the things you're hanging from them. And so the mass effect is pretty small. But if you made a pulley out of steel and tried doing these things with the same weights hanging from it, even though the friction wouldn't be any more, you would have a bigger effect of the mass of the pulley. Okay, so first, massless. That's the warm-up problem. Yeah. Because it has mass and some radius, it takes a force to cause an angular acceleration of the pulley. That's what's going on. You have to, so in this case, we're not doing it in terms of energy, but you can think of it as like it doesn't take any energy to get that rotating. Now, because that has mass and radius, it takes, some of the energy is taken up by making that pulley spin. Okay, so since this pulley is massless, the tension is the same all along the pulley, all along the cable, I mean. The tension is the same at all points along the cable. So now we can just isolate the two different masses. So first I'll do a free body diagram of the big mass. There's a weight force of big M, G, and an upward force of T. And Newton's second law says 0T plus 0 negative big mg equal to big M times the acceleration, which is only going to be in the y direction. The x equation doesn't give us anything, but the y equation gives us our first useful equation. I guess I'll call it 1. It says T minus MA is equal to big MG. So those are all big M's in that. What are the constants and what are the variables? The constants here are big M and G. Variables are T and A. And so we have one useful equation, two variables. Can't solve. Yep. That's a good idea. Yes, they will be. So yeah, let's call that A capital N. And then a free body diagram of the smaller mass.
If you do acceleration, right? Can you just write the acceleration all the same? Oh, it's the same variable?
They're not going to be the same. Yes, that's what we're going to do at the end, is we're going to write them all in terms of the same variable. I'm going to start out like this. This is a reasonable way to do it. You know, like you can get kind of overwhelmed if right from the start you're trying to think about how the motion has to be constrained and stuff. Just write down what you know in as many variables as you need, and then at the end you can count and see how many relationships you need between these variables geometrically. So there's a weight down of small mg. The cable force up is T again. And so Newton's second law says 0T plus 0 negative little mg is equal to 0 little m times the vector 0. I'll call this one A little m. The x equation doesn't give us anything. So our second useful equation says T minus little m AM is equal to little mg. And so now the variables we have are T, A big M, A little m. And so we have three variables, two equations, and so we need one geometric relationship, one constraint equation. And where does that constraint equation come from? Yeah, you know, there's a relationship between those two accelerations. We know that if this one goes down an inch, this one goes up an inch. So A big M is equal to negative A little m. So that's the third one, and I'll substitute that in. Into 1 and 2. And we get T plus big M times A little m is equal to big mg.
So you're using big M.
So we're going to solve for the acceleration of the little mass. But yeah, big M is in there. But that's a constant. That's not a variable. The second equation says T minus little m times AM is equal to little mg. And I guess I'll subtract these two equations, and we get 0 plus the quantity big M plus little m times AM is equal to the quantity big M plus little m G. I saw these. So what would be? Oh, this should be positive. Yes. So this looks right, doesn't it? And then, yeah, I have to change this one. But these look right. And then when I subtract, then this is big M minus M. And so the acceleration of the little mass is equal to big M minus little m over big M plus little m times G. And that's up. Okay, so that's massless. That didn't use any rigid body stuff. That was particle kinetics. Any questions about that one? And as those, you can see that as the little mass gets closer to the big mass, the acceleration goes to zero, like you would expect. Once they're the same mass, they just hang there. Okay, so now we're going to deal with a pulley. With a radius, capital R, and a moment of inertia about the center. I sub C. Since the pulley isn't massless this time, the tension in the cable changes along its length. Or, really just across the pulley. So the tension in the cable is different on the two sides of the pulley. Okay, so I'm going to start with a free body diagram of big mass. We have big mg, and this time the cable tension isn't the same everywhere, so we have to differentiate. So I'm going to call this the cable, the tension on this side, T sub big M. And then Newton's second law says 0 T sub big M plus 0 negative big mg is equal to big M times the acceleration vector 0 A sub big M. This gives us one useful equation, T sub big M minus big mg. Let me rearrange that. So I'll call it T sub big M minus big M A sub big M is equal to big M times G. Okay, in this, what are the constants and what are the variables? The constants here are big M and G. The variables are T sub big M and A sub big M. Okay, so we have two variables, one equation. Can't solve that. Now, free body diagram of the little mass. The weight is little mg. The force up isn't the same. We'll call T sub little m. And so Newton's second law says 0 T sub m plus 0 negative mg is equal to little m times the acceleration vector 0 a sub little m. The x equation doesn't help. The y equation gives us that T sub little m minus little m a sub little m is equal to little m g. The constants now, we've also included this little m now, so we have a big M, a little m, and a g. And the variables are T sub big M, T sub little m, A sub big M, and A sub little m. Okay, so we have four variables and two equations. At this point, in the case where we weren't including the mass, how many variables and how many equations did we have? Remember? We had two equations and three variables, so we needed one constraint equation. This time we need two constraint equations. What about the constraint equation that we used last time? Does that still hold? If you pull one an inch down, does the other one go an inch up? Yes, it does. It does. That's just a property of that cable not stretching. Yeah, we don't know anything about the forces, but we do know that we can use that same equation we used last time. So equation 3 says A sub big M is equal to negative A sub little m. Now what? Well, we're doing this problem. Yeah, exactly. So we're doing this problem in the rigid body section. So it seems like a reasonable guess that somehow rigid body relationships are going to come into this. And what we're going to use is the fact that, you know, the accelerations of these points. Okay, so, well, there's a relationship between the accelerations, so we're going to do it in terms of little m, and the angular acceleration of the pulley. That was true in the massless case too, we just didn't need it. So what's the relationship here? Well, we know that so yeah, we know that the tangential acceleration, okay, so look at the picture and imagine what's happening here. Okay, the acceleration of, say, this point okay, is the tangential acceleration of that point on the pulley. Okay, those two things have to match. And so, so we know that the acceleration, little m, has to be equal to alpha cross r from this equation. But we're not using this because we know that that a sub m is vertical only. That centripetal part is towards the center. Okay, so a sub, and this is a vector, so a sub m is equal to 0, 0, alpha, crossed with the r vector to that point where the little m cable touches the pulley. Okay, so what's the r vector from the center of this circle to this point here? It's in the positive x direction, r. So r, 0, 0. And so that tells us that 0, a sub m, 0. Yeah. And we haven't used it yet, I don't think, have we? Oh, okay, let's use uppercase. Yeah, there's just one. Let's call it uppercase. So this is equal to, if you take that cross product, you get 0, r alpha 0. And so that gives us a fourth equation that says am minus r alpha is equal to 0. Okay, so now let's think again about the constants and the variables. What do we have? So the constants that we've used are big M. Have we used that yet? Yes. Little m, g, and r. And now let's think about the variables. What we're hoping is now that we have 4 equations, you know, we still have 4 variables and we can solve this system. But it ain't going to happen. Because what are the variables so far? We have the t's, the accelerations, but now we've introduced this new variable. Okay, so with this constraint equation, we just sort of treaded water. So now we have 4 equations, 5 variables. Exactly. So now what we're going to do, so that didn't immediately look like it helped what we're trying to do. Now we can do a rigid body kinetics analysis of the pulley. The moment equation is going to include this alpha. And now we can get our 5th equation without adding any new variables. We know the pulley's moment of inertia, so that we're going to use that instead. Yep. But if it was a disk, then yeah, you could do it from the mass. Yeah. So now we're doing it in a general way where this could represent any round shape. It could have a square cut out of the middle, or, you know, it could be a ring or a sphere or whatever. So for the fifth equation, rigid body kinetics of the pulley. Okay, so does the pulley have, so let's just go through the steps. Does the pulley have a fixed point? What is it? The center, yep. So the about point is the center. So then this is where we usually calculate the moment of inertia around the fixed point. We're told that the moment of inertia about the center is I sub c. Third is the free body diagram. So there's the pulley. We have some unknown force in the middle. I'll call that, well, I'll just call it F. We have a weight acting down from the center of, this isn't going to come into our equations, but I'll call it mass of pulley times weight. And then we have a tension on this side, T sub little m, and a tension on this side, T sub big M. Any questions about that free body diagram? Okay, so now step 4, we're going to calculate the row vector, force vector, and moment. This force F and the weight act at the center. They act at the about point. And so they all have 0 row vector. So we have no row vector times F, cross with this F vector, gives 0 moment. No row vector crossed with the weight gives no moment. And then we have those 2 cable forces. Cable force big M, what's the row vector for that force? Negative R0, yep. So negative R0. The force vector is 0, negative T sub big M. And so the cross product is R T sub big M. And then what's the row vector for the other cable force? That's positive R0. The force vector is 0, negative T sub little m. And that cross product gives negative R T sub little m. Fifth. Do we need that? Nope. We only need Newton's second law if there's no fixed point. It would introduce new variables because we'd have to deal with these forces at the. That's what we're going to use, yes. So the rotational Newton's second law says R T sub big M minus R T sub little m is equal to I sub c times alpha. And so our, what, fifth equation says R T sub big M minus R T sub little m minus I sub c alpha is equal to 0. Okay, so now this is sort of a mess. But we are going to, okay, so let's substitute 3 into 1 and 2. So we'll sub in equation number 3 and rewrite the equations. Equation 1 says T big minus big, T sub big M minus big M A sub big M is equal to big M AG. And I'm going to substitute in little m for A big M there. So we have T sub big M plus big M A sub little m is equal to big M G. And the second equation says T sub little m minus little m A sub little m is equal to little m G. Then the third equation, which was previously our fourth one, says A little m minus R alpha is 0. And our last equation says R T sub big M minus R T sub little m minus I sub c alpha is equal to 0. Okay, so I'm going to, what we're trying to find A sub m. So equation 4 here says tension big M is equal to tension little m plus I sub c over R alpha. Right? Does that look right? And now I'm going to rewrite these equations again. So we have T little m plus I sub c over R alpha plus big M A little m is equal to big M G. And then we have T little m minus little m A little m is equal to mg. And then we have A little m minus R alpha is equal to 0. Equation 3 says alpha is equal to a little m over r. So rewrite. So the first equation says t little m plus I sub c over r squared am plus big M a little m is equal to big mg. And the second equation says Tm minus m a little m is equal to little mg. And now I'll subtract these two. And you get I sub c over r squared. So the quantity I sub c over r squared plus big M plus little m times a little m is equal to the quantity m minus little m g. And so a sub little m is equal to the quantity big M minus little m times g over I sub c over r squared plus big M plus little m. Okay, so what happens to the acceleration as the mass moment of inertia of the pulley increases? Yeah, as the mass moment of inertia of the pulley increases, the acceleration gets smaller. And as the mass moment of inertia goes to 0, the acceleration limits to what we got in the massless case. I forgot how much algebra that is. That was a lot of you watching me do algebra. But anyway, it's still cool, right? I mean, I think this is probably for most of you the first time in a class that you've seen what the effect is of giving the pulley some resistance to rotation. And this is what happens. Any questions about that? Okay, well, let's stop there. And next time I'll do the Pinewood Derby thing, and then I'll give you a problem or two to work on together. Kinetics problem, rigid body kinetics problem. And then we'll be done with rigid body kinetics. And after spring break, we'll start doing linkages, basically like the dynamics version of structures.